Howdy, everybody. Hope you're doing well whenever you are. We're here for the recap of Advent Code 2025. I think it was a good year. I had lots of fun doing it. I think it ended with a bang. It was that was a really fun ending. I think there were definitely some good days where it felt easy. And when I say easy, I mean I think it's because if you've been following with the channel, I've been trying to do a lot of this puzzling. So we did Everybody Codes before, and we've been solving problems before. And I think that really helped me a lot. And so that made some of the days feel a lot easier. So again, if there were hard days for you, don't feel like, oh man, I'm dumb or something like that, because I had hard days too. One of the hardest days was the math day. I kind of struggled with the math. That took me some time to figure out. We're actually going to talk about it in this one because there's two other ways to solve it. And by other ways, I just mean two different ways to do it. So we'll talk about that in the video some more. But the hope of the recap is I picked three things out that I think are worth looking at just to, improve and get better. And so hopefully you will find those interesting. A little sad that there were only 12 days, but I totally understand. If someone asked me to do this, it would be a nightmare. It would be very hard to do. It had to be a full-time job, I think, to get it to be able to pull these things out, I imagine. And especially with like the number of people, right? It's one thing if you're just doing like a small puzzle a week in a magazine that people may send in some submissions and you look at them and whatnot, but setting up the whole infrastructure and doing that stuff, I recognize is totally hard. So props to the Advent Code team for getting that done. And I think that's amazing that we got 12 wonderful days. I don't know, just in this introduction, that's probably all I want to say about how the days went. I think, well, I will say again, like I felt like weakest at the math. So, but I still even felt like those days were worthwhile because they helped me learn, right? Help me learn and grow. And, that's what we're trying to do in the channel is to, be better puzzlers. And I think that will translate into better programmers overall. So, let's dive into it. The first day I wanted to talk about was day 6. And not necessarily because day 6 was like particularly hard. Sorry, I don't have my browser up here. It wasn't a particularly hard day, but I mean, it was. I guess I could see how it was kind of hard because you were doing math. You had to do some math that was kind of funny. If you remember, the way it was is you had these columns where you were doing math, and so you had to pick out what's 1 2 3 times 4 5 times 6, what's 3 2 8 plus 64 plus 98, and then you like sum them all together. And then part 2 got harder because it was now you have to do them columnar. So like it was 4 plus 431 plus 623 like this. And so that required a little extra effort. But most of it, like what I guess what I'm saying is most of the problem was actually more of like a parsing problem as opposed to an algorithm problem, if that makes sense. Although I guess one could argue that a parsing problem is an algorithm problem. So, to each their own, I guess. The reason though I want to talk about it is for performance reasons. So not everyone's into performance, and if you're not into performance, that's fine. Some days you're just worried about, can I just solve this problem, right? And so if you solve it and it takes a few seconds to run, but you're all like, oh, I got it, I think that's great. But I do think it's worthwhile. Oh, my camera's actually off a little bit I did some deep cleaning. My camera's off a little bit, so that's funny. Anyway, the people like to think about performance. So this is a performance one. And so I just want to talk to you about like thinking about performance, right? That in real life, you probably don't care to optimize something like this solution, because I think my original solution solved in like 100 microseconds or something like that. So if you can solve a problem in 100 microseconds or whatever, like that's clearly fast, right? It's fast enough that the user probably isn't going to notice, right? Like if you go to google.com and you wait for like 5 seconds, it's one thing. But if you wait for like 250 milliseconds, it's barely noticeable, right? We're out of like the AOL days when it took like 3 minutes to, get a picture from the news or whatever. Like, so, but milliseconds is definitely fine. So when you say microseconds, you say, oh, do I need to even worry about this? And the answer is probably no, but it depends what you're doing, right? And so I just thought I'd share some of my performance tips, especially if you're coming from Rust, maybe some things to think about. So you can see I was able to get it down to, 15, 16 microseconds solving the problem. Whereas before it was probably, I actually don't remember the exact values, but it was like in the 50 to 100 microseconds. So that's quite an improvement. We're talking like 4 to 8 times faster, somewhere in that range. So how do you go about doing that? Well, my original solution was just to use split and then to collect values. And then I had like 4 vectors. And then I would just like go through the columns of the vectors and solve them. And that's really fast. In this one, it's like not much harder. Like if you think about how the way you solve this is you kind of like, I think I may have worked backwards for these positions, and then knew that the following 3 were like the math ones, or look for the, start from the end and go to here. And now I would look at the columns and make the values and then do whatever the operation was. But you're still kind of like splitting and looking at it. And that takes time, right? So it's not insignificant to allocate vectors and to put values in the vectors when you're talking about microseconds, right? In your regular work, if you're using Rust, I collect vectors all the time. And, it's only in like the most performant things when I don't. You can get away without collecting vectors. In fact, in this one, you can actually get away without doing anything. And why do I say that? The problem is actually structured as a grid, like as a character list, right? So you've got new lines that separate the columns, and then, but everything is like neatly organized is maybe the way to say it. Like if it was outlined specifically, right? If you've ever dealt with like a flat file before, where like each row and each column have like very specific delineations, where they say like the first field is 50 characters and the second is 30 and the third is 5 or whatever. It looks a lot like that, right? Which means you can actually treat the file as a grid and just work on the grid, right? So the first optimization I made was, well, I don't actually have to parse the input, right? I can just use that grid as part of the solution. And so that's what I do, right? Instead of trying to parse the input, I say, hey, just give me the vec of U8s. Notice I'm using U8s here. That you can think about that as like a byte or an ASCII character. That is a limitation of this, right? Is you have to be able to use ASCII characters. In our case, we're just worried about the numbers 0 through 9, and then add or multiply. So if you had to worry about like, Cyrillic or accent marks or any type of Unicode, this solution's no longer going to work, right? You'd have to do something different. You could include this as a string, I suppose, but it's a little bit harder to index into strings and stuff like that. In this case, though, we don't have to, so we can just treat it as a vec of U8. We don't even have to parse by new lines. And why do I say that? Well, you can actually, again, because the lines are of equal length, once you find the first new line, you can now kind of calculate a stride. At least this, I think it's called a stride. That's the way I learned it, is like you now know the stride of the line is whatever, say it's 20 characters. And so every 20 characters, there's a new line, right? So if you wanted to get this character, you would know it was 2 lines down plus 1, 2, 3 characters in, right? Obviously, you're 0 indexing, but I hope that makes sense. So you would just say, oh, it's 2 times the stride plus 3 characters, and that will get me this specific character right here. So now by just doing a little bit of math, you can immediately go to that position and figure it out. So that's what we do here. We figure out how long each line will be. What is our stride? And that's us just looking for the first new line, and then we add 1, right? Because the 1 puts us to the next line, if that makes sense. And then we just need to figure out how many lines there are, and that will tell us where the row is for the operations. Right down here, we want to know where the last row is, so we kind of want to calculate based, and we can do this now with just math, right? Because we know the total length of the string, and we know how many strides, we know how long each line is, how many what the stride is, and so we can figure out where this line starts. That's what we're interested in, right? Where does this one start? And the reason for that is because we want to be able to calculate it, right? So we can start here and go. I actually think we work backwards, but you go here and then you go here, and now you know everything in that column is a thing. So this code is going to look a little bit more complicated, but you know, we're just doing math, right? We're like, how many lines are there? Now we know the data lines are like the count of the lines -1, and the op line is this, right? So we're creating a slice of the operator line, which is the data times the number of strides, right? The data lines times the number of strides, and it's the end. So now ops contains this last line right here, right? And so now we just can do some looping, right? And what we're going to do is we're going to loop through the ops, and maybe it will help if I draw this a little bit, right? So let me do that really quick. But we're going to start it. We're going to iterate through the ops doing an R position, and the idea behind the R position is we're going to look for characters that aren't ASCII white space. So one thing I want you to think about in Rust is sometimes these functions that you call look like they might be expensive, but they're actually, I can't remember the exact terminology. I think they call them zero cost abstraction. And the idea behind zero cost abstraction is it's going to turn it into machine code that isn't going to affect performance. So even though we're doing this like R position and finding the first one in the reverse that's not one of these, that's actually really fast. It's able to figure it out for us. Okay. How do I want to show this? Maybe I'll do this, 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 this. Those are some big numbers. Okay, basically what we're gonna, so we've collected like this line right here, right? Now we have this line is our ops. And we've calculated our stride, right? And so we now know how many lines exactly there are. And so we're going to call this rpos position, rpos, where it's not spaces. Like this is what we're doing. We're saying rpos where it's not space. And what this is going to have the effect of doing is like searching, finding here and here and here. And why do we do this? Because once we've found this, we now know up here what all the values are in our array. And then we can just, we can do, we now know like the position here, and now it's just math. It does take time to think about, right? It's not as simple as splitting, collecting, and just indexing over each group, but it is just math. So given enough time, I believe, you know, anyone could figure it out. But so once we've got this, now we just have to find the 64, 23, 314, and multiply, right? And we're just going to do that over and over again, right? We do this rpos, it's going to take us here, it's going to take us here, it's going to take us here. And notice we're going to do it in a while, because we're moving the end of the thing, and we're going to do it until we've collected them all. Eventually, we'll have done this one right here. We'll have done this rpos, and there'll be nothing left over here, right? There's nothing left over here. And so we know we're done. And then it's just a matter of, again, doing the math, right? So we say if it's a asterisk, we're multiplying, so we start with 1, otherwise we start with 0, and then we're going to go through each of the rows. We know how many rows there are, right? So we know there's 3, so we're going to go through these 3 things and find those values. And again, like I said, it's a little, it looks complicated, but it's actually just math, right? We're going to do our row number times our stride plus our cur, right? So that gives us, that's this value right here. So let's say we're working on line 1. It's going to be 1 times our stride plus our cur position, right? So that's going to put us right here, right? And then we're going to iter until, as long as we're getting ASCII digits. Again, it's helpful that the puzzler kind of did this for us, but we're basically going to go until we get an ASCII digit. So we stop right there, and now we know the number is, well, we could just produce a string, or we could fold, right? And basically we take what we start with, times it by 10, and add the digit, right? So this is the effect of saying turn. So say it's a 9 minus the byte 0 is going to return 9. We turn it into a U size and add that to our thing. Again, this is one of those cool features of Rust. One might say, oh, is that fold particularly slow? We could do this in a for loop, but the zero cost abstraction of Rust will likely make this fold just as efficient as our own for loop. The only time it wouldn't is if there's special stuff you're doing in here, so Rust can't do that zero cost abstraction effectively. But otherwise, so that's going to give us this value, and now we're either going to start multiplying or adding. And we just do that over and over and over again until we've gone through all the sections. You know, we set our end to cur, so now the next rpos is going to start, you know, right here and go this way, right, till it finds this one. We're going to do rpos space, right? We're just going to do that till we find the next one. We're going to do it over and over again and solve the problem. What this has the effect of doing is we've done no additional allocating on the stack except for trivial variables like in our loops. Right? There's a potential to say, like, we have this block right here. We could move this out if we wanted, but Rust is usually smart enough, the compiler is, to say like, oh, this is like an important variable. I can like keep track of this on, you know, in a place where it's important, and you know, keep it tight. Again, you could do more performance testing. You could look at the assembly code and say, oh, maybe it's not doing that. And so what can I do to get it to use that, get it to put it somewhere? But what's happening in this loop is like very tight and very specific, and you're just doing indexing. We're not allocating new giant blocks of code or anything like that. And that's how you get from 100 microseconds to 15 microseconds. If you ever like have watched videos about Advent-to-Code, or not Advent-to-Code, the 1 billion row challenge and stuff like that, a lot of it evolves around how can I minimize allocations. In the case of, and obviously for that one, it was parallel processing and then worrying about the hash. But the first things you wanted to fix was how do I minimize allocations, you know, and things like that. And how do I go through the data effectively? And fortunately, Rust has ways to do that. Now, there are ways that we could potentially do these like rpos searches faster. For example, SIMD is it allows you to like search in parallel, because our most modern processors have simultaneous check operations. And so you can basically, like, instead of checking one character at a time, you can check like 8 or 16 or it may be 16 is the maximum in this case because it's a byte, but the idea is you can do it in parallel. So that might offer you some help, but that would be a very micro optimization at this point, right? This is all to say there's definitely ways that you could improve it. But part 2 actually looks the same, right? The outer logic is the same, where we get the stride, we get the line information. Now we're looping on our pauses. Just the difference is now we're counting. We got to do columns to create the numbers as opposed to rows to create the numbers. But the logic is the same, and it solves really fast. And so this is just to say, if you're interested in performance programming and speed programming, from by speed I mean like eking the most out of your solution, Rust has some cool ways to do it. And so just the things that I would focus on are how can you minimize the allocations you have to do, and how can you effectively like enumerate and index into the original input to get the values you need. And that can help you a lot. There's problems where parallel processing, again, will help, where SIMD would help. I think it would be fun. Let me know if you'd like to do this. Is I can kind of show you how to use perf with Rust. And so you can do your analysis and figure out. I mean, that's what I did. Well, I should say, obviously, using the zero cost allocation was a big thing, but you can use perf to see how to improve it and where to look for improvement. So there you go. There's one of the days that I thought was like worthwhile of like looking at, is like, how do you like bulk, how do you like build in additional performance? And Rust definitely has tools to do that. Everyone says Rust is like blazingly fast, right? That's kind of like the joke. But you still have to allocate things on the stack. You still have to do stuff. The reason why people say that, and I realize a lot of times it's kind of said jokingly, is again because you get the zero cost abstractions a lot of the time. It's also like meant to be a performant language, as opposed to, so that comes with constraints like the memory safety and stuff like that. So but it does give you the tools to make fast stuff as well. And I think that's what's cool, right? And I don't have to do crazy things. I can just say, oh, I'm still going to do an R position, but it's going to be pretty fast. And again, maybe you replace this R position with a SIMD search. That's great. It's cool that Rust has that. I will say that some of their SIMD stuff in the standard library is still in the nightly. It's not like ready for prime time, if that makes sense. But there are crates that will do it for you if you're really interested in it. So anyway, let me know if you're interested in SIMD and running perf. We can definitely do that. Let's move on to day 10. So what was day 10? This was the math one. And again, like I said, I normally don't actually like these days because I'm really, and again, it's just because I'm bad at the math. Okay. So if you remember, you had like these buttons, and the buttons affected certain lights. And in part 1, it wasn't too tough because it was like a lights out game where you just kind of, this would turn on buttons 1 and 3, or toggle, I should say, buttons 1 or 3. This would toggle button 2, so on and so forth. So, and what happens in part 2 is you're now given like numbers, and you're trying to find those numbers. And if you remember, increment them correctly, right? So like this, now 1 and 3 would increment spots 1 and 3 by 1, right? And so you're trying to get to this target value and the minimum number of presses. And this is one, if I remember, I actually struggled a bit and I needed to get a hint. And so I talked to AI and it gave me a hint about linear programming or linear algebra. And so I was like, oh, that's right. And so I went and found, because it is like you could build a matrix out of this, right? Did I show that? Where was that stuff? Right here, right? So you can build a matrix out of the buttons and out of the values you're looking for, and then you can try and solve for them, right? So you can see here, I think in the video I walk through, here's how you do the Gaussian elimination, and as you're doing that, you can track your free or independent variables, and those are then the ones that you got to search for to solve the problem. So that was a lot of work, but I did feel good about my solution. I felt like it was a good end to the or a good end for day 10 to solve it that way. It was a lot of work for me though. It took a lot of effort. And at some point someone was all like, oh, you could just use Z3. And I don't remember if it was a commenter or if we had read it in Reddit. But I was like, oh, that's a cool idea. We could use Z3 to solve this. Because if you think about this problem, it's actually, it is a constraint problem, right? You're trying to find to minimize the number of buttons you push to solve this thing. And so you can ask yourself, well, can you solve this? So that's one solution we're going to look at is Z3, where basically you put this matrix in. I guess it's technically this matrix was the original one. Is that right? You put this matrix into it. Essentially, you put this matrix into it, and then you say go minimize on the number of times you press these buttons right here. I think the columns were the buttons, right? Go minimize the number of times you press the column. And then someone had mentioned, excuse me, there's another library called Highs, which is right here, and it's a high performance software for linear optimization. It's a linear programming thing. Essentially, the way it works is, it's I mean, maybe it's in the same domain as Z3, but Z3 is a much more general constraint solver. This one is more meant for problems that look like this. If you can order your problem, if your problem looks like this, then it will solve it for you. So I'll show you both of those solutions. So thank you, by the way, to the commenters who pointed this out, because I think it's good to learn about other solutions and other ways to do it. And we'll look at them and we'll just compare and contrast them and see what you think. The Highs is relatively new, and so it actually, I found it maybe I did it wrong, but it didn't have the same performance as Z3. It was a little bit slower. And that could just be my ineptitudes, or it could be that Highs is, still relatively new. And so the optimizations aren't there. And again, I recognize part of that too is that Highs maybe isn't focused on its Rust bindings. And so someone's just like building Rust bindings for it. But I'll show you that code. So let's do that. Well, first let's run it. And I'll show you the differences. So here's my original P2 solution. You can see I was able to solve it in 5 milliseconds, which is, when the last one solved in microseconds, maybe you're like, but 5 milliseconds feels fast to me. It could definitely be improved though. Here's the Z3 solution. It was able to do it in about 60, and then the Highs was able to do about 110. So it was about twice as slow as the Z3 solution. But remember, these solutions aren't meant to be like optimal, because they're generalized constraint solvers, as they're called SATs or SMPs. But like the general idea is there is like you give them a set of constraints and it will try and meet those criteria based on, do you want to minimize it, or do you just want to ask is it solvable, or maximize it, right? I should say at this moment, I am working on a series. It'll be maybe 4 or 5 videos on Z3 itself. So look for that in the coming week. Hopefully you'll enjoy that, because I think it is a useful tool and it would be worth looking at. So what does this code look like? Well, Remember maybe I should just describe it really quick. How these things work is the idea is you want to like build a constraint. And I'm going to do this at like a very, very high level because again, I'm doing these videos. But you may say to yourself x plus y equals 3, and then you say 2x plus I don't know, y equals 5. And now it's gonna, you have this, and now you want to ask yourself, okay, can you solve for x and y, right? And if you've done this math before, you can kind of figure it out, right? You move things around, maybe you do subtraction or addition or whatever to like get to a solution. But what you probably end up coming up with is, I think with this one, is x is 2 and y is 1, right? 2 plus 1 is 3, and then 4 plus 1 is 5. And, so you get 2, 1 is the solution, right? The way that you solve this by hand is like very, I don't know. You kind of do it with your mind, if that makes sense. You've learned some like algorithms to kind of do it, but you kind of like fidget around and you get an intuition for it, right? When you're looking at the puzzle or the problem, you may say, "Oh, it's probably easier for me to like I'll move the x over here and then plug it into here and then solve for it," right? You've learned some of those tools. The way a constraint solver works is slightly different, but not like totally out of the nature of that. But you give it constraints. So you say, hey solver, x plus y equals 3, and 2x plus y equals 5. And then you say, what is x, y? And it'll do its work, and then it will say, hey, it's 2, 1. But this is a relatively easy one. You can give it crazy ones, right? Like you can give it hundreds of parameters and hundreds of stuff, and then it will figure it out for you. The things you need to do is you need to tell it what the variables are and what the constraints are. And then you need to tell it how what you're solving for. And so in our case, our variables are the number of button presses, right? And our constraints are the buttons to voltages, right? And so what we want to tell the solver to is minimize buttons pressed. Again, if this isn't making a ton of sense, I'm going to try and do a video series. But like at a high level, these are the 3 things you want to give these like solvers. And so you just got to figure out what these are. And if you can figure out what these are, you can give it the problem and it will solve it for you. And this one works very well, but you could potentially solve, I've thought about it for a little while. There's a possibility that you could use this to solve many, if not most, of the days of Advent of code. So just the way that they work is kind of crazy, but it makes it so that you could kind of solve many, if not most. Obviously, you have to be able to give it the variables. So if it's like day 6, where it's a parsing problem, right? If you're worried about like the parsing of the day, like how do you parse this thing? It's probably not going to help you that way. But if you're worried about, how do I like manage these constraints, this will be great. So I got a link here. You can read more or look for my video. We also do it in parallel, just so it solves a little bit faster. But what do? Well, we got to create our optimizer because we're optimizing. And then we need to add our variables and our constraints, right? So that's what we're doing here. We create our voltages, right? They all start at 0. And then we create our buttons and we say, hey, every time you press this button, and it has to be greater than 0, these are some of the constraints you have to add, right? Because it might add a negative constraint to the value. And again, because we're using integers, we won't get a half, but we're saying, hey, it has to be greater than 0. And then we're going to tell it, hey, for each of the wires that the button goes to, add that to our joltages. So we say the joltage at this position is equal to the current joltage plus this button's variable, right? This button value. If you look at it, it actually looks like code, right? That's what I think is cool about Z3 is you're using these Z3 values, and under the hood, you're just doing the math, right? You're doing joltages equals joltages plus this button variable, but it's rigging it up to create the constraint tree, the AST, to solve this, right? So, but you can see we've made our joltages, we've made our buttons, we've linked our buttons to the joltages that they go to, and then we've made all the joltages sum to the button presses, right? So we've told the optimizer that the way that you figure out what the joltage should be equal to the machine value joltage, right? So we've told it that's this part right here. Like in this one, it's that part right there, right? We've told it we're looking for 3 and 5. Right? So we've given it these values, and now we're telling it we assert that these values should be 3 and 5. Okay? We've also asserted that the buttons have to be greater than 0. But then the last thing we need to do is just tell the optimizer that we're trying to minimize the total of presses, right? So how do we do that? Well, we say for each of the buttons, we want to minimize their presses, right? And again, these buttons are coming from Z3. I think this is really cool because it looks like this. I should say Z3 did not used to look like this. You had a config and you were adding variables. It was much more like, I don't know. It felt a little kludgy to use in the Rust ecosystem, but I think they've done a lot to fix that, and that makes it really exciting, right? Because we can just use itters and folds. You can see me using folds and things like that. We're mapping things, and we can use like actual operators to get to the solution. But again, what are we doing here? We create our optimizer, we create our joltages, we create our buttons and link them to the joltages. Then we assert that we're looking for these specific values as the joltages. And then we say that the number of button presses is equal to, all the sum of all the times you pressed each of the buttons. And we want to minimize that. That's what we're looking to minimize. So we're going right here, we're saying, hey, I want you to find the minimum values that meet the constraint. This one isn't a great one. So maybe we go back here and look at it a little bit. No, day 10. So we've told the optimizer, these are the values we're looking for. And then each one of these, maybe I should do this. These are the values we're looking for. And then each of these is equivalent to a button press. And we want you to minimize these to get to these. I hope that makes sense. That's what we're telling it to do. And then we just, that's what this is. We say, hey, minimize that. And then we go check to see if it's solved. And if it is, we can get the value. And this looks a little crazy to get the value because you have to get the model, you unwrap it, you evaluate the total presses, right? You're saying, hey, give me the variable back that is the total presses, and then turn it into an I64, and then we unwrap it and do it as a U size, and that gives us the result. So again, we're not doing a lot of error checking here. It would be a little bit more complicated if you were, but that's how you solve it in Z3, which I actually think is really cool. And the thing is the times that I'd used Z3 in the past is it felt, again, like I said, like a little difficult to like translate their function calls into like code. But this is really cool, right? I can iter map, I can iter enumerate map, I can iter for each, I can enumerate for each, I can iter fold, do very normal Rust things with these values, and the Z3 will properly build the syntax tree for you. So anyway, that felt really cool. How does the highs thing look in comparison? It's actually quite the same, right? It's pretty similar. The difference is you're not creating an optimizer. You're telling it, oh, it's a column problem, which again is like it's saying, hey, it's this type of problem. And then you do the same thing. We're going to add our rows, our joltages. So in this case, the way you do it is you say, what are our rows, our constraints? And the constraints are our joltages. So we say, hey, I need you to add a row for this specific joltage. They allow you to do ranges. So it can it could be like a range of values, and then you it uses those ranges. In our case, we only have a specific one, so we're only going for one. And that's why we have that there. But again, we've just created our joltages, and then we need to add our buttons for each of those joltages, right? So we go through each of the buttons, we figure out which joltages that button affects, and add them to this factors list. And then we just tell highs, hey, add this integer column with those factors, right? So it starts from 0 to, blah, 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 and do it for these factors. And what it then does is it adds a 1 in each of those positions, right? It basically says the way to think about it is you're building this again, right? So you're building these columns for each of those things. Okay. And then we just tell it the same thing. We say, hey, optimize this solution, minimize it. And the optimization we want is to minimize it. Notice the S's as opposed to the Z's up here. I guess you have to get used to British English if you want to use this. But you're doing S's. But otherwise, you just say, hey, solve it. And then you say, hey, if it solved correctly, if it found a solution, give me the value back. And you'll get the value back. And there you go. You can see all three of them return the correct thing. So there's my original solution, which is obviously faster because I can do the Gaussian elimination, and then I can do the find on the free variables. These optimizers are meant for more generalized problems, but they both solve comparatively fast, right? I mean, this is still a really fast solve, especially considering you're doing it on I don't remember the total number, but it was in the hundreds or something along those. It may have been 1,000. Was there 1,000 of them? I don't remember. There was a lot of them. And so anyway, there it is. There's your two other ways to solve it. How would I rate these? I don't know if you want to give me a thumbs up or down. I think the highs works pretty cool. I haven't worked with it a lot. And so I don't feel comfortable just saying oh yeah, go out and use it. But for this problem, it definitely feels solvable, right? You add your constraints, you add your columns to those constraints, you tell it to solve it, and it solves it, right? So I think that's very cool. Again, it's not as it doesn't seem as performant as Z3, but a lot of work has been put into Z3, and so I can see it just being a difference between the time invested and the performance done on it. I could easily foresee, and again, maybe I did this wrong, and so I haven't optimized it well enough. I haven't optimized it well enough to get an optimal solution to it, but it was still I think it was worth learning about, so it's something in my toolkit. I was really impressed with Z3. Again, it's changed since I last used it significantly. I think I actually solved it just a month ago, but I was using a problem a month ago, but I was using some older, I think maybe I was using an older library version or something. I don't know. This felt really nice, and it felt performant, right? No one's going to knock you for being able to solve this problem in 50 milliseconds. So that felt cool. So Z3, I think, is a really cool thing. Definitely something worth looking into, especially if you're trying to, how can I solve a problem faster? I think you could probably, if you're familiar enough with Z3, you could write this solution substantially faster than my Gaussian elimination one up here. I feel proud of my Gaussian elimination solution. I tried to follow the Wikipedia, the steps of doing it, and so I felt like I got there in a good solution, and then I could solve the problem in the end. But I could really see Z3 being helpful for days like this. Thinking about like solving problems in the future, I don't suspect I'll use Z3 for like a video, because it doesn't feel it doesn't feel good to me to just say, oh, I just use Z3, here's my Z3 code. That's probably not super helpful from like a learning and growing perspective. But I definitely think days where you could solve it with the Z3, I'll probably add that as an additional solution. I'll say, oh, look, this is also solvable with Z3. So if you wanted to do it that way, here's what it might look like. So I think that's what I might do with these days in the future, is if I say, I'm going to be looking out for them. And if those days are there, I think, I'll just call them out. Or if I miss one and you say, hey, you could solve that with Z3 or highs, maybe I'll come back to those and look at them in a little bit. Okay, day 11. This one was actually, in my mind, easier than day 10, though again, it varies. If you remember, you kind of like create this graph of like networks, and then you're trying to solve, you're trying to like traverse the network. And in part 2, it becomes difficult because you have to find the FFT and the DAC, and it's actually pretty difficult to like find that. If you remember, what happens is the graph just explodes, right? You start out by, oops, I don't want to do that. You start out just searching from here where you are, right? You're right here and you're going to here. You get there pretty fast. But now it wants you to start from here to go all the way across, and you have to have hit FFT and DAC. And it wants you to say how many paths are there in total. Well, it just becomes absurdly large and like impossible to solve. So you really have to do some kind of like DFS with memoization type thing. And so I'll show you my solution. And that's exactly what I did, right? I did dynamic programming with like the default values, and I said, hey, find DAC, find server to DAC, and DAC to FFT, and FFT to out, right? That was my solution to it, is to DP it that way. If you remember, there was like we actually found a solution. Multiple people did this, but the one that we looked at was from Jonathan Paulson, so I call it DP Paulson. And he actually uses Python, and he used the Python crate, or not, the Python standard library has a func_tools cache, which allows you to like essentially memoize a solution. And so I thought I'd just show you the equivalent of that in Rust. So the way that this solution works is you need to track your neighbor, or you need to have your neighbors list. But then you just say, what is your current position? And have you seen DAC? And have you seen FFT? And then you return a usize. So in the original implementation, I think the way that I implemented this is I kind of had to like go back up, or I had to keep track of my own list of like memoized values when I like copy and pasted it over. But you can use the cached crate, okay? You do have to do a little bit of work to use it in Rust, because we actually, if you think about what's happening here, and you can see it up here, we don't want to like we don't want to cache our neighbors. That's just like a lookup list, right? So you could make an argument, oh, I'm going to make this like a global variable using like oncelock or something like that. And then it's not a part of the function itself. But the cached crate actually allows you to use this, right? let's just look at the crate so you can see what it is. Here's what it is. You basically just say, hey, cache this value, and the macro has the effect of just wrapping your function in a caching utility, and it will likely be, you know, some type of hash map that hashes the value. It might be something slightly different under the hood, but I imagine it's probably a somewhat specialized hash map. But you just tell it, hey, cache this, and now you've cached Fibonacci numbers, so you can keep asking it relatively large values, and if you've already pre-calculated some of it, you don't have to calculate that additional stuff again, right? But in our case, we need to do some special stuff because we don't want to cache this part of it. So we actually can tell it, though, what we want to cache. We're going to say, hey, I want you to cache a string, a bool, and a bool. And that's going to come from cur, scene DAC, and scene FFT. And this is going to have the effect of being the lookup for the cache, right? So what it's going to do is wrap your code and say, hey, if this function is ever called, I'm going to go check and see if it's already been called. And if it has, I'm gonna just return that value. So now it will say, I'm gonna look, is cur, scene DAC, and scene FFT in my lookup list? And if it is, I'll just return that answer. I don't have to solve it again. If it's not, I'll run this function, get its results, and then save it in the cache. So if you've done memoizing before, you'll know that that's the gist of how memoizing works, but the cache crate does that for you. So you're going from what it used to be was you had, well, it does that sometimes. You'd have your FN of like memo func or whatever, and then you would pass it like A, B, C, and you would say you'd also have your memo in here. You'd say if M of A, B, C, like if there's a value in there, you would then say, you know, return M of A, C. Otherwise, you know, do work, and then you would say M of A, B, C equals work, right? And then you just like loop through this, right? This is like the general idea of memoizing. You check, right? Cache. Otherwise, you do work, and then you save cache. Okay, so the cached function does this for you. So now your new function with the cached is you just say cache, and then you say fn demo func a c, and then you say do work, return work. And what happens is like the caching tool. So this caching tool will do this part for you and this part for you. You don't have to worry about it. It will do it for you. And that's all that's changed, right? So just I hope that makes sense. This is a cool crate that you can use. If your logic is simpler, for example, again, we are looking here at this Fibonacci, you can just say, hey, cache this. And this is more akin to how it works in Python. In Rust, because we have like typing and we have lifetimes and stuff like that, sometimes it becomes a little difficult. And so you have to do something like this where you say, hey, here's the 3 keys that I actually want you to do the cache on, and then here's the values that I want you to do a cache on. Then it will do it for you. And the effect of this is we don't have to worry about the memoization anymore. We hand it over to the cache. We just do the work. So if you remember what that was we check if we've reached the end. If we have, and we've seen DAC and seen FFT, we return 1, otherwise we return 0. Otherwise, we just go through all the neighbors and call this function again. We do it over and over again. And the cached will pick up that thing, right? So I actually don't think I've run this to see if it's faster. It's actually slightly faster than my solution. And why is that? I actually DP 6 times. So the joke is I DP 6 times because I'm going through, like, I'm trying, there's like, you can switch DAC and FFT. And so I try it DAC and FFT way, and then I try the FFT and DAC way. Only one of them's going to work and return a value. The other one's going to return 0. So I just pick the one that has the value, and that's my solution. Whereas this way is doing the entire tree and just tracking those values, whether you've seen FFT or DAC, and including those in. So, okay, that's the last thing I wanted to talk about, was this cached tool. So if you haven't used the cached crate before, obviously you can just memo yourself whenever you're using DP, but you can also use this cached crate to leverage it. And then, you don't have to worry about the caching part. I will say, though, it's not as fire and forget as Python is. The Python one is you literally just slap the @cached on it, and suddenly you're caching stuff. Even if you're passing stuff you don't necessarily expect to pass, it figures it out for you. It may not be super optimal, but you just slap it on there and it works. We do have to think about it a little bit more because we're using Rust. So you may have to, like, work out what you want your key and how you're going to, turn that into the key. But it's at least reasonable, right? It's a cool proc macro that you can use, a cool crate that you can use to kind of like wrap your function in a caching utility. And so I don't have a problem with using this, right? It definitely is like a great way to, as opposed to me passing these values each time. In fact, that might be a fun exercise to do, is can I just turn this one in this DP solution into to using the cached one, because it's essentially the same, right? I just have the cur in the end and I'm looking for these things. It's potentially faster, right? Because I'm just it's faster in the sense that I don't have to worry about this stuff. I still have to worry about it, but I'm only worrying about my current end values right here, and not also whether or not I've seen those things. There you go. Hopefully that helped. You got the cache crate now in your pocket. Another thing that you can use. So to recap, what did we talk about today? Hyper optimization. Like, do you want to spend a lot of time digging in? Rust definitely has some tools to do that, right? So, if you want to, like, eke out the most performance you can, there's tools to do that in Rust, as well as the Rust ecosystem, right? Obviously, like, perf is like a Linux tool, but Windows, Mac OS, they have similar tools that you can use to, like, check the performance of how your thing works. It's really easy to look at assembly code in Rust, like what the assembly code produced is, because you're using LLVM under the hood, and so LLVM will spit out that stuff. And then Rust, again, it has the zero cost abstraction for a lot of it, so you can actually make code that is still relatively readable, but still eke out all the performance. Okay, so what else did we talk about? We talked about different utilities, different crates that you can use to solve constraint problems, Z3 and highs. Those are cool libraries that you can use. Keep them in your mind for further years, or if you're going back to solve previous years, those might be an option when you have these kind of constraint style problems. It can be hard to determine, is it a constraint problem? So that would be something to like work on, and I feel like I need to work on. Again, I think I told you it wasn't clear to me that it was a linear algebra problem immediately, and so I had to get the hint of, oh, it's a linear algebra problem, and then I was able to solve it. So there's that. And then day 3 is, look for other crates that can help you. We've talked before about itertools. We've talked about Rayon. I think I've done videos on like Tokyo. And now, something like the cached crate. Surely we haven't, well, maybe we've talked about Serde before, Serd, whatever it's called. These are all really cool, like external libraries that aren't specifically the standard library, that can really help you, right? Whenever you are working on a language, it's important to understand the ecosystem of like, what are the tools that other people are using? Often because they're powerful tools, and so it's just good to know what the powerful tools are. But also because I think it helps you understand like what's available to you for your language, and to solve your own problems or to solve problems at work or whatever. So always look for some of these tools. The cached crate is one of them, so keep that in mind. I'll just say in conclusion, if any of this sounded interesting, I already plan on doing the Z3 stuff, but maybe we can also look into like performance courses and stuff like that. How do we eke out the most performance? The other thing that we can look at is, other libraries and stuff that you're interested in. So if you have any ideas or thoughts about what things might be worth looking at, I'll be happy to look at them with you. I'm almost sure you could give me a library and I will give you an Advent to Code problem or an Everybody Codes problem or a LeetCode problem that we can go through to try and solve it. So anyway, love your feedback. It was great to this is one of the things I'll say in conclusion. I love doing these puzzles because I feel like there's a good community out there. There's people trying to solve the problems, people struggling, people helping each other, working together to get to a solution. Lots of beers were offered. So I don't get out much. I enjoy being a little homebody in my town in the middle of nowhere. But and so it's nice to have that community where I feel like I can talk to people about solving problems, getting help with each other, learning and growing. So I really appreciate all your comments and working with you all. It's truly a lot of fun, right? And so thank you very much. And I think that's it. It was a wonderful Advent to Code. So we'll talk to you next time. Bye, everybody.